Okay, Tēnā koutou katoa, Morena. Welcome to this webinar titled Introduction to the STRAND Project and Exploring Sources of Uncertainty. We have 5 guest speakers contributing to today's talk. Dr. Murray Kadzau, who is a scientific programmer at RTIS at the University of Otago. Professor Anthony Moore, who is a professor of Geographical Information Science at the University of Otago. Dr. Quinn Nguyen, who is a climate change economist at GNS Science. Professor Ivan Diaz-Rainey, who is a professor of finance at Griffith University, Australia. And Dr. Maxime Rio, who is a data science engineer at NESI and a data scientist at NEVA. Before I hand it over to our speakers for the day, quick round of housekeeping notes. This webinar is being recorded. So do make sure to mute your microphones. And if you're not comfortable with your screen being captured on cameras, just switch them off. All good. We do have a QA doc that we'll be using through the course of the webinar. I will share that link now on chat. That is just to make sure that if you have any comments or questions through the course of the presentation, please feel free to capture them. They can be anonymous if you want them to be. And at the end, we'll make sure to go through all of them. And with that, I will hand it over to Ivan.
Kia ora, tēnā koutou katoa. Thank you very much, Nisha. It's a real pleasure to be here today. Let me just make sure I share my screen. So look, I'll start off the presentation. So I'm going to be sort of providing a sort of big picture overview of the project. It's a strand, we call it STRAND. It has lots of meanings, obviously, because those of you from work on the coastal side will obviously get the strand, that side of it. But in the finance literature, STRAND, we talk about stranded assets, the possibility that climate change may cause assets to become highly written down or entirely worthless, or actually become liabilities rather than assets. It's a Marsden Fund project, so we are running till pretty much the end of the year, and it's really highly interdisciplinary work. And yeah, it's definitely been an exciting project to be associated with. So as I said, I'll start off. I'll provide a big picture overview. So I was originally the lead PI on this, and about a year and a half ago, I moved to Australia. And so Tony took over as being lead PI. He was always the co-PI. And so he'll talk the second part of it. And then the team, Murray, Maxine, and Quinn, will talk about work stream 2, where NESI came into the picture. So yeah, we'll talk about one work stream, which is around scenario uncertainty and modeling uncertainty. And we modeled that, but we didn't factor in data uncertainty. And that's where NESI came in and the team comes in. So that's roughly the order of play. Yeah, so that's the official title of the project. So should I stay or should I go? Climate change risks to property values across space and time, and the related implications to financial stability. So I guess if we unpick that, it sort of starts off with sort of hazards, vulnerability and exposure leading to risk. And then we have high frequency data. We've got CoreLogic's real estate data. So we need to translate that to some sort of, that risk into some sort of damage function. And then we have, high granularity data effect on real estate. And then the idea is to aggregate it to the banking system. So yeah, the focus is very much on coastal hazards. So, and when I came to this naively as a finance researcher, I thought we'd be able to just take the sort of hazard exposure models that the physical scientists have, and I imagined naively that they would have all the models sorted and the complex interaction between these physical hazards would be resolved. But the reality is there's still a lot of science to be done at the interaction of the various hazards that are there. So sea level rise, rising groundwater, storm surges, extreme precipitation, and as I sort of intimated there, it really is the often the interplay between these that cause the most severe episodes of risk. And of course, because of them and because of climate change, return periods for natural coastal hazards are declining. And as a finance person, obviously, you know, in New Zealand, not 65% of the population live very close to the sea. But yeah, as a finance person, really, our wealth is very much concentrated in real estate. So 85% of individual wealth is concentrated in real estate. And we have what we call a bank-based financial system. So unlike Australia, where a lot of financing happens through capital markets, most of the financing in New Zealand happens through our big four banks. And they have a huge exposure to the domestic real estate. So 60% of their loan portfolio, their assets, their balance sheet is is tied to domestic real estate. So this has what we call macro and micro prudential considerations from a financial stability. So appreciate most of you are not from the finance side. So this means really that you know, we ask the question, could climate change and the interaction of these hazards cause an individual bank to fall over? And, you know, if it's a very big bank, could it cause the whole system to fall over? So one of the things you'll have seen is that Reserve Bank of New Zealand has gone from being not interested in this area. And I recall having a deputy governor come and give lectures to my banking class. And I asked them, this was some 6-7 years ago, you know, what do you think about climate risk? He just looked at me like I had grown a third head. But now to actually being quite a leader in this space. So it's amazing how fast things have moved. So, you know, RBNZ has been doing some really interesting related stress testing around climate risk with the banks. And that partly comes building on mandatory climate related disclosures that has been brought into New Zealand, and reporting I think starts this year for last year. So you know there's been a policy world underpinning this, and actually, so when we started this research, really, it was really, you know, it was not meant to have a huge translation element. It was really meant to be very blue skies. But because of this regulatory environment, as the project has progressed, there's been a huge amount of interest from policymakers and so on. Yeah, look, it's a really interdisciplinary team. So I was at Otago, as I said, till a year and a half ago now at Griffith. So we've got Greg Bedecker from Bedecker Scientific and Simon Cox from GNS Science. So, you know, we have a hydrogeologist, a climatologist, and Tony, who's the PI, now the lead PI in the School of Surveying, and myself. The person that's done all the work and puts the slides together and puts herself at the bottom is Quinn. She's done all the hard work. She's really the data scientist that the STRAND Marsden Fund Project funded until she moved to GNS Science recently. And of course, Murray has come in to help us out on the data uncertainty side of it. And we have the next generation of Quinn in Owen Aitken, who is a student we're incorporating into the team and has been working on one of the work streams. So really interdisciplinary team. Honestly, I think we spent the first 6 months finding a common language. You know, that wasn't easy, but we now, I think, have a really high functioning team that works well together, and you will see over the next 12 to 18 months a lot of output from this project. So we have what we call a theoretical framework, and on the top side we have the physical side. I'm just keeping an eye on the time, and on the bottom side we have a stylized view of what the market response, the real estate response might be. And, this is a very simple model, but it helps to highlight that, we have rising groundwater probably because of sea level rise. And also because of climate change, we have increased frequency and increased severity of high precipitation events. And anything that takes us above the dotted line causes flooding. So this is, you see the declining return periods, and it's a function of both the increased frequency of precipitation and severity of precipitation, but also because of the association between sea level rise and groundwater. And so that translates to, you have a flooding. And so this is partly based on the experience we had in South Dunedin, where we had a flood in 2015. We modeled that from a house price response, and there was a large correction, a drop of about 15%, maybe slightly more, 20%. But it gradually recovered. So perhaps analogous to what might have happened with the earthquakes in Christchurch. And so, insurance markets recover and mortgage markets will be able to cope with severe but infrequent events. The issue is once that frequency increases, and how does the housing market respond? A lot of the modeling that's been done to understand the impact of climate change, flooding related risks in New Zealand has taken permanent inundation as a point at which the housing market gets affected. But if you understand markets, they're forward looking. We buy a house and we usually stay in it anywhere between at least 7 years, 7 to 20 odd years, right? So, and, so markets are forward looking. That's something that a lot of people perhaps don't fully capture. So, an underlying hypothesis here is that the house is going to be stranded well before permanent inundation, and that's going to happen due to increased frequency of periodic rather than permanent flooding. This is a chart that our hydrogeologist Simon put together. I'm just keeping an eye on the time. And really, it gets more complex every time that this chart gets put up. And it really shows the complex interaction of many of the different hazards and a lot of the physical phenomenon. We've got storm surges, we've got groundwater, we've got precipitation, we've got fluvial runoff. So, it's a complex picture. And then, if you add climate change on top of that, then, you've got this depth to groundwater and there's a loss of subsurface storage. So there's a complex interaction of hazards. And that's been part of what the team has been working on. And that's one of the work streams. So there's a multi-hazard flood model, and Simon has just sort of pinged that paper. It's close to being submitted, and Greg and the discussions between Greg and Simon have been invaluable in that. In particular, I was surprised that the interaction, and I'm not surprised now, but at the time I was surprised how linking groundwater and surface water and precipitation would be so incredibly complex, but it really is, and I'm not surprised. Then the work stream that Tony is going to talk about is a deterministic uncertainty. So we explore scenario uncertainty and methodological choices. And then there's the NESI part where we add data uncertainty to that. We also use one of the project partners is NIWA. We use their extreme sea level models, accounting for sea level rise to do a national stress test. So we have a working paper for that, and so that's like a national analysis of how extreme sea levels might affect financial stability. So we take that all the way up to banking stability, and we're in the process of we have a working paper, and I'm going to start presenting that soon. And then there's a theoretical framework that I just showed you earlier, which we're looking to formalize. We also have virtualization stream. So that's where Owen Aitken, who I mentioned earlier, is part of the team, and he's trying to find an effective way to communicate some of the complex ideas, especially around uncertainty, to a broader audience and in particular stakeholders and the public. And last but not least, there's CARI, but that's Tony is the expert on CARI, which is a multi-criteria coastal risk index, which starts us thinking about, amongst other things, data uncertainty. So I hand over now to Tony.
Thanks, Ivan. Just checking you can all hear me. All good. Thanks. And thank you all. Thanks to for the invite to talk here and at this arena. I thought I'd start with CARI, the Coastal Asset Risk Index, because it actually encompasses the full broad range of factors involved in what we're doing. In doing this, we're trying to establish risk, coastal asset risk, and you can regard that as a goal. And for risk, we take a definition here: the potential for consequences where something of value is at stake and where the outcome is uncertain, from the IPCC. And it encompasses both physical and human worlds. And although the main thrust of this presentation is about the physical, I thought I'll just kind of give you an insight as to how we're dealing with human factors. In going towards that goal, there are several objectives, a lot of which are covered by the IPCC. I want to draw attention to the middle two there. We've got exposure, which in that risk definition could be that's representing something of value that could be lost or damaged. We're talking about human assets, cultural assets, financial assets that are at risk. And they're at risk from hazards. And hazards are these agents of change, of drastic change, of course, sea level rise, groundwater, storm surges, and so on. And they raise the stakes for these assets. And you can see examples of these objectives underneath here, and they're listed as criteria. The nomenclature is significant. I'll go into that in the next slide. And then we've got two other objectives, which could be regarded as mitigating factors to this central hazard exposure link. We've got vulnerability, which really kind of affects basically how exposed your assets are. Things like elevation and slope at the coastal zone kind of in the presence of a hazard can really affect the criticality, the actual degree of effect of the hazard. As well as stuff like sea defences and soil type, sea defences defending against the hazard and so on. And then we've got resilience, which is kind of human structures in place to mitigate the effects of hazards. For instance, in case of evacuation, the presence of roads is important. The integration of community and the amount of able-bodied people is important too, to help out in the case of an emergency. So bear this three-tiered diagram in mind. So we've got at the top goal, then the objectives that define a goal and the criteria within each objective. And if we go move on to the next slide, where CARI comes in, CARI is a multi-criteria decision-making tool where experts come in and they actually weigh up each of those objectives relative to each other in pairwise weighting. So they could say that, yes, okay, hazards is twice as important as exposure in the definition of risk. And then within each of these are those sets of criteria. So if you remember, under vulnerability, there was elevation and slope. And so experts can weigh up the relative importance of elevation regarding as opposed to slope. And then these go into an analytical hierarchy process. The central tool in this multi-criteria evaluation to come up with an index score, a weighting, if you like. Then that weighting in the geospatial world, where I come from, gets combined with spatial data, normalized spatial data, in order to come up with kind of index maps for each of those 4 objectives. And at the end, those are combined to provide a risk index map. Next slide, please. To give you an idea about my words, when I talk about spatial data, this is what went into a pilot project with some last year spatial modeling and analysis students in Otago, where I'm based. And so we got 8 spatial layers. This is the extracted Otago coast from the Waitaki in the north to the Catlins in the south. Dunedin and the Otago Peninsula is somewhere around here. Sorry, I'm just gesticulating with with my pointer, but you can only see Ivan's. Thank you, Ivan. And just from left to right, we've got elevation slope to vulnerability criteria, groundwater, distance to coast, to hazard criteria, distance to buildings, personal income, that's 2 exposure criteria, and finally, distance to roads and also proportionate work. These are 2 resilience criteria, okay? You'll notice patterns, they've been normalized to a scale of 0 to 1, and they've been normalized so that 1 is actually represents most risk in this, okay? And you'll notice that some are based on census units, for instance, the personal income and proportionate work. And so we've got very coarse spatial units there. Others, you take my word for it, are based on 1 meter elevation data, for instance. So bear that in mind. We've got data of varying qualities and varying what are known as veracities. By that latter term, I mean some data are directly measuring what they purport to measure, like elevation. Others, like, for instance, distance to coast, is a surrogate, and it's kind of 1 conceptual step away from what it's trying to measure, which is really susceptibility to sea level rise. Okay, let's move on. So one last results screen for this carry. So if you combine it all together through that analytical hierarchy process, the multi-criteria evaluation, then you get a risk index of this. Bear in mind, this is based on kind of a very small selection of non-expert data. It's just a pilot project just to kind of give the tool a bit of a run. So we've got varying risk. Dark is low risk, light is high risk. And as expected, the coastal areas are in the main light. You can see South Dunedin here in the Dunedin inset reflected as high risk. And perhaps more useful, we can start to play around with some risk thresholds in order to kind of isolate some of the areas and make them more apparent. So here I'm playing around with 0.8 risk threshold. You can see the scale here on the left-hand side, and 0.825. So here's some initial results. We want to bring this to the real experts in the end. This will happen later this year. The financial, the coastal experts, the local government experts who can kind of bring their expert knowledge and weightings with a wider set of criteria. And besides which, we want to also bring in some of that data quality and data veracity information, because this result over here on the left is highly subject to the quality of data, and we wanted to reflect that in the process. And just to keep it short, that's what's going on the right-hand side here. So now I move from a kind of a wide conceptual human and physical world to the main thrust of this presentation, which is all about mainly modeling in the physical world. And so we return to Ivan's slide. He talked about the schematic on the left-hand side. All I want to kind of reflect on here is really behind defining this, what goes on in the future. speculating and getting our results, there are a lot of sources of uncertainty from scenarios. So, for instance, the IPCC have basically put out a range of climate change scenarios, and we could choose any one of them. The IPCC are not the only source of scenarios, so we also got NZ sea rise as well. So the source of projection is also something that could be changed, adding to the uncertainty. And then there are a raft of methodological choices we could tweak. Our input elevation can affect the results a lot, depending on whether we use, say, mean sea level or mean high water springs as our kind of level to define flood, and whether we adopt what's known as a bathtub model or a geometric model. That leads to widely different results. I'll show you a few of those in the coming slides. We can play around with kind of coarse and fine spatial resolutions. They lead to different results. And we can basically play around with exposure functions or damage functions, which is more in the financial world and really relates to how much can a property or a house be flooded in terms of area before it's deemed basically flooded and subject to the graph that you see here. Okay, let's move on. So data uncertainty at the bottom there is the area that Maxime, Quinn, and Murray will deal with later. Okay. So we come to that main deterministic uncertainty work stream. And on the right here, we have that list of choices methodologically and list of scenario sources and alternative scenarios. You get more information here. If, for instance, you get the list of IPCC scenarios listed at the top here. You get a list of the two alternative data sources, choice between a 15-year-old LiDAR dataset and one that's more recent. And we get those inundation models, alternative inundation models we use that use variously mean sea level or mean high water springs, or the bathtub method, or the geometric stroke groundwater-based method. We get a range of resolutions in the spatial world, and we get quite a lot of alternative damage functions down here. Of course, I won't go through them all. I just want to reflect that in red here are what we chose to be the baseline scenario. And we really assess variations relative to that baseline. And I'll just give you a selection just before going to the next slide, just highlighting a couple of our source data sets. This here on the left-hand side is the 2021 LiDAR elevation, showing you the area that we're studying. South Dunedin is this blue basin, pretty much bounded by sand dunes to the south, raised reclaimed land abutting Otago Harbour to the northeast, and everywhere else there are hills, lots of hills. So basically, it's a protected area from the sea directly, but as we'll see, there are other means by which the sea can encroach on this area. And the other one is basically a representation of the rateable value of land. So from the most valuable land in the southwest in St. Clair in red to less valuable land basically everywhere else, but particularly there are areas of South Dunedin, north-south Dunedin, that are the least valuable, relatively speaking. Okay. And here's some results. So I'm only going to concentrate on the baseline, which is the first map you see here. And what we see is basically degree of flooding. You can see the scale here. And so the baseline, there's not much flooding going on at all, except over here in the area closest to the university campus in the north part of Otago Harbour. We can see, though, what happens. So this is what happens when those baseline conditions are adopted in all those methodological choices and all those scenarios. But if we tweak a bit, so for instance, if we swap out the scenario that was baseline, which was the SSP2 for the most extreme SSP5, then we can see the relative increase in flooding that happens relative to baseline. Moving on to the next one, if we swap out the source of scenario from IPCC to NZ sea rise, then we see slightly more flooding in the kind of Musselburgh, Andersons Bay area, which Ivan's pointing to. If we use an alternative, and so next three, this one here on the right-hand side and the first two on the next row down, are what happens if you use different inundation models. So from the baseline model of mean sea level bathtub model, if we then moved into a more nuanced geometric or model based on a varying groundwater surface, then we get a flooding scenario which kind of matches what we've observed from previous flooding incidents, like for instance the 215 flood, in that the floodwater, due to proximity of groundwater to the surface, really gets very far inland. And I'm really pointing to the kind of northwesterly extent of flooding here, which is actually the most affected in flooding incidents, as we've observed in the past. And then we move to the mean high water springs, a kind of raised sea level, if you like, relative to scenarios. And we got the groundwater and the coastal bathtub scenarios there. If we go to a coarser DEM, then we've got a change relative to baseline, more flooding areas there. And sorry, this next one is actually an alternative source of DEM. The last one is actually an alternative resolution of DEM, moving from 1 to 15 meter resolution. The point is that as we move on to the next slide, that altering even one parameter alters the results drastically, and therein lies the uncertainty in a deterministic sense. And I'm aware that I'm running towards the end of my time, so I'll just show us here as an illustration of what happens if we consider altering the damage or exposure functions. You can see, depending on whether, let's say, we deem a property as flooded, if one cell within the property is flooded at ground depth. So 0 meter depth really means that we're not adding say a 30 centimeter representation of the house floor, which is one of our assumptions. We can see that if one cell is flooded, basically leads to a property being flooded, then we have this extent of flooding. Alternatively, if we regard the house as being flooded 10% in area and a kind of 30 centimeter raising of the house area, then we can see there's only a modest flooding in the eastern part of the area there. So again, the message is that depending on what damage function we use, there are a wide range of results. And we take that into what Owen's doing with visualization. And what Owen's doing as part of his master's and part of STRAND is that he's taking all of this data and he's actually exploring different visualization methods. What you see here is a kind of visualization method by itself. Alternative scenarios that actually displayed side by side, but Owen is actually kind of playing around with virtual reality and also metaphors to express visualization. A well-known one in the geospatial world is fog. So basically, the more uncertain you are about an area, the more fog there is over that area, and you don't see the data because the data is, for want of a better word, crap. Not crap in quality, but basically uncertain. Okay. And non-foggy areas are basically where you're more certain about the data. So the next slide actually shows some of these things. We see the fog metaphor map over here from when it was originally published by Alan McEachran, a well-known geovisualization scientist. We see some attempts to bring fog into the virtual world here. And the next graphic will show you where Owen wants to go. Given that we're talking about flooding, a metaphorically apt way to depict it might be to put our virtual world underwater and to have turbidity, the amount of sediment in the water acts as a kind of water fog, if you like. So we'll be playing around with that. And one last one, this is how far Owen's got so far. He's basically bringing in a straightforward representation of uncertainty by color into virtual environments. He's using Unity. And with that, so I'll pass on to the other main thrust of uncertainty, and that is in a kind of bringing stochasticity and NESI facilities. Thank you. Cheers.
Cool. Thanks, Tony. If we go to the next slide there, Ivan. Cool. So where I sort of come in and we're going to delve sort of more into the methodological side of things and where we brought NESI in. And so this was where we're sort of modeling the sources of the uncertainty. So as Tony had mentioned, there's all these different sources. We had scenario, we've got land elevation, sea level predictions, spatial resolutions, and these are all coming together in sort of a combinatorial or permutatorial manner that we're going to try to explore where the parameters sort of matter. And so what sort of initially happened was there were a lot of models that need to be done, and initially this project was referred to through the NESI consultancy, but as part of that it was identified that there were some preliminary skills that we needed to bring for the researchers before we could sort of begin the NESI consultancy part of things. And so that's where I, as part of research teaching IT support at Otago, sort of came in for the initial upskilling and development work through the project. And I kind of got embedded in the project and worked alongside Quinn to convert her code and scripts that she had generated to sort of introduce some version control, some command line skills, get some of those initial resource profiling and compute estimates. And we had a lot of design and tweaking off the initial compute workflow. If we go to the next slide. So the initial approach that we had was we're looking at the entirety of South Dunedin, and to get sort of an idea of the uncertainty, we were going to model South Dunedin 5,000 times, so an iteration in a Monte Carlo approach where we're generating 5,000 iterations of a particular, I'll call it a scenario model. And after we'd done the generation of these 5,000 models, we have a summarization step. So we can sort of put an upper and lower bounds and create a distribution of things. But what we had here was our initial approach was fine for sort of the initial generation of the iterations, but we had a real struggling point where we tried to summarize them. So the amount of data that this approach generated was fairly large. And when we were trying to summarize things, this is where we had a bit of an issue and couldn't quite get things to work. So we changed our approach. And if we go to our next slide, please. We sort of changed from modeling South Dunedin as a whole 5,000 times to what we call the cookie cutter approach. So rather than doing the entirety of South Dunedin, we would take a residential property and sort of punch through our different areas so that we got the area corresponding to that property, and then we would model the scenario within that area. And we'd do that 5,000 times, and then we'd summarize the property. So we were sort of breaking the problem up into many smaller pieces, and ultimately we were looking at about 25,000 model scenarios to get through. So all of those different combinations of the uncertainties, we wanted to see where they all went. And ultimately we were looking at about 12.5 million iterations in order to generate the data across all of this. And we wanted to get a sense of where was going to be flooded and where was not. One of the downsides to this particular approach was that some particular scenarios we couldn't implement in a way that we could get working. So things like the coastal inundation models, because we didn't have the connectedness to the coast, we sort of had to delay modeling on those for that moment. So if we go to the next slide, please. Cool. So the underlying architecture that we had for generating the data was for each property, we had 2 steps. The first one, we were going to generate the flood maps. So we'd load in the spatial data, we'd generate our 5,000 simulations, and we'd save it out as a single TIFF file. And then the second stage of this was that we would process these simulations, and we'd calculate a range of statistics across the property, and then ultimately we'd sort of binarize simulations. So we'd apply a couple of thresholds to determine whether or not a property had been flooded or had not been flooded. And as part of this as well, we through this procedure, we worked out that we didn't need to run every possible scenario, and in fact we managed to cut that 25,000 scenarios down to roughly 5,000. So in the process of going through these iterations, we'd sort of reduce the amount of compute area that we needed to get through. And then once we sort of established this particular way or workflow, we were ready to take this to the NESI consultancy team and really start optimizing things so that when we ran big with all of our scenarios, we could do this in an efficient manner. So I'll pass over to Maxime to go through what we did with the NESI team.
Thank you, Murray. So before I dig into all the profiling, I will say a few words about one of the key tools we used, which is Dask. So Dask is a Python library dedicated for parallel and distributed computing. It's really a Swiss Army knife when it comes to doing parallel processing. And in particular here, we'll first focus on the second step, so the aggregation of the summary statistics for a given property over the different simulations. And for that, we were using the Dask array interface, which is depicted on the bottom right. And think about it of when you use a Dask array compared to a regular NumPy array in Python, you can chunk it, so split it in small pieces, and then the computation on each of these chunks can be run in parallel, and that's how you increase the throughput of your computation. Next slide, please. Okay, so first step is we try to optimize, as I said, the computation of the statistics. And to improve this, the first thing we need to do is to do a bit of profiling. And what was very nice in this consultancy is there was well-defined test cases, so we could look at it, profile, and find bottlenecks and improve. And here the profiling revealed 2 first small issues. One, there was a large memory usage at the very beginning. Data was loaded when it was not supposed to be. And also the behavior, which should have been parallel, so using multiple cores to run, was actually serial. And I want to highlight what you see on the right with what's called the Dask dashboard to explain a bit more about this. So the Dask dashboard is a very helpful web app that lets you investigate how your computation are running in parallel or not, in that case with Dask. And the central panel on the x-axis is time, on the y-axis are different workers that are supposed to work in parallel. And ideally, when everything is running in parallel, you should see a big green rectangle. And here you see a lot of tiny stripes. And actually, that means that if we zoom in and look a bit more, we would see actually that at a given time, there's only one worker working, and all of them, the other ones are waiting. So we want to believe it's parallel, but actually that was a serial behavior. So we fixed these two issues, and thanks to that, for computing the statistics of an average property using 2 cores, we went from 45 minutes to a bit more than 3 minutes. And also we managed to fix the memory consumption from 7 gigabytes to less than a gigabyte. And based on that, we did some further improvements, and we managed to get the largest properties, so the one which were the most time consuming, to be able to compute the statistics in under a minute and a half, and using only 7 gigabytes. So that was all great. Next slide, please. But then we thought like, okay, this is nice to have optimized task, but do we need task? I love this tool, really, but sometimes complexity can get in your way for doing additional optimizations. So what we looked there is, okay, we can do everything in NumPy without parallelism, so using only one core, and can we have something as performant? And it turned out that almost, which means that, for example, by changing a bit the code, we managed to reduce the memory consumption. So for this large property case I was talking about, we were not even using 9 gigabytes anymore of memory, but only 5. And although it was a bit slower, so now it was taking 2 minutes instead of a minute and a half, we were only using one core. And remember, we have to process more than 6,000 properties in parallel, which means that overall, we'll be using less resources. Next slide, please. Okay, so I just said we need to process 6,000 properties. And so now we've done the optimization of one script, the aggregation script. So how do we orchestrate all of them to run on more than 6,000 properties, and as Murray mentioned, about 5,000 scenarios. And this is where we brought in a workflow management system called SnakeMake, and which has a lot of qualities, and among them, it can track dependencies. So for example, automatically you define and say like, okay, first you run the simulation with my first script, and then you run the summarization with second script, and it knows when to start each of the different tasks when the previous one have stopped. It also knows how to speak the HPC language. So in our case on NACI and also on the University of Otago HPC, we're using the Slurm scheduler. So it's capable of submitting jobs on your behalf. Combined with Conda, we can make also something very portable, and we'll see later that that was key to the success of this part of the project. And finally, it has a very nice property of resilience in the sense that if things starts to fail, or if you need to interrupt to fix something, it will keep track of what are the tasks which have been achieved. And then when you restart it, it will not recompute all the properties and scenarios that have been computed so far, but only it will finish the one that were remaining. There was a few glitches here, a few problems that we had to fix. First is for the small properties, it takes very little time to compute their statistics, and that's something usually a Slurm cluster does not really like. It does not really like jobs that are less than a few seconds. But SnakeMake has a very nice property that you can group tasks together. So instead of saying, hey, I want to do these millions of tasks that are super short-lived, you say, hey, actually, you'll take this bunch of tasks and you'll make them one job on Slurm. But still with that, we ran into another issue, which was the amount of tasks themselves, so the numbers of property times the number of scenarios, were a bit too much for SnakeMake to be able to handle. And we'll see how we address that after. Next slide, please. Yeah, thanks. But at that stage, we pause and say like, okay, we need to do a little benchmark to see if you want to run the everything, how much time will it take? And so we did a bit of a test with 6,000 properties, which corresponds to and only for one scenario. And roughly it took about, let's see, 2 hours using 500 cores on Mahuika and NACI's HPC. And we knew at that time we could maybe get about 2,500 cores. And that means under an optimistic scenario, it will take 100 days to complete the whole thing, which was a bit too much. So we had to think about, okay, what can we improve even more? Next slide, please. And this is where we thought like, okay, we'll use Dask actually, but to do some parallelism at another scale as the one before. So before we were using Dask within the summarization, the aggregation. Now we'll use Dask to compute for one scenario all the properties. But before I explain how we get there, there's a first thing to explain, which is how we can save a bit of time by first merging the two steps. So as we said before, there is a bit of simulation and then aggregation. But when you do this as two separate steps, you need to save files after the first step and reload them after. And this is a bit of IOs or input-outputs, which takes time. So first, we combine these two. And then the second thing we realized is for the small properties, what takes most of the time for the computation is actually to load the shapefile. And the shapefile is a big file that defines, as Murray was mentioning, this cookie cutter approach, so the footprint of each property. So when you process one small property, you need to load the whole shapefile, get the footprint of this little property, and that takes most of the time. The rest is nothing. So when we actually did the parallelism across properties with Dask, we were able to load the shapefile only once and then process all the properties in parallel. And that's what you see on the right-hand side with the bottom right graph, which is we load the data only once, then we do all the properties in parallel using Dask, and then we save the results sequentially at the end. And using this strategy of loading shapefile only once, we managed with less cores, so only 200 cores. One scenario was taking 14 minutes instead of 2 hours. Next slide, please. Okay, so with that, we were equipped to do the big run. And as I mentioned previously, we made sure that the workflow and the computing environment, the software stack was portable, thanks to Conda and SnakeMake profiles, and which meant that we could leverage the compute resources of the NESI Mavica HPC, and also in parallel all the RTS Otago Aoraki HPC. And again, we were using exactly the same code, but we could say, okay, these scenarios will be running on one platform, these scenarios on the other platform. We did a larger test scale just to see how much time the whole thing should take. And with 16 scenarios now of 6,000 properties, it took only half an hour. So we thought like, okay, yes, 6 days, it's done. Now, real life happened, and there's more things than only pressing run, and you need to transfer data, you need people to be available to double check the data, and there's all sort of things. Which means that in the end it took 5 weeks, but it was still much better than what we got at the beginning. Next slide, please. Okay, I'll just conclude my part on a few lessons learned during this collaboration. The first one is, I think the success of this part of the project was really due to the collaborative aspects between the researcher, Quen, the RTIS REC Murray, and myself from NESI, because we each had a different perspective on the project and skill set, and we were able to collaborate on this. And for some of us were translating the jargon for the other one, so I think it was a very nice collaboration on that. The second step, when you want to, for more the optimization part of things, is having tests. So having a nice constrained test case helps to do systematic profiling, finding the bottlenecks and improving. And I hope that's what I've conveyed in before, is all of these improvements were really systematic in a sense that we always took an example, ran it, find the bottlenecks, remove the bottlenecks, rinse, repeat. That's how you get the best out of the system. The next thing is also remove complexity. Sometimes I'm guilty of this, of wanting to use the shiny new tool or Dask because I love Dask and I want to put it in every consultancy, but sometimes it's not the right tool, and it's important to try to see where complexity is useful and where you need a bit something simpler and you will have better performances. A few other things is, as Murray mentioned, one way to get better performances sometimes is to change the problem, and reducing the amount of scenarios to compute was also a way to achieve faster results. And then when you optimize, first optimize the single task in a very parallel piece of code. And once you have your single task very optimize, you try to optimize the parallel aspect. And here was how to find the best scheduler. And I'm using it in a bit of a vague sense, like Dask was a scheduler and SnakeMake is also a scheduler. And we find the right granularity for each of them to work well. And finally, the importance of having portable code and workflows so you can leverage every hardware at hand. add on that note, I'll stop here.
Cool, wonderful, Maxine. Yeah, so look, I think we're running out of time, so I'll try and wrap up, Nisha, so that maybe we have a couple of minutes for questions. But yeah, this is just a summary of the work stream. As I said, we now have 2 or 3 working papers, 3 working papers close to submission, some more analysis that we're going to be doing, so not least the probabilistic analysis, we still need to do that, and the theory element. But so, as I said, there's going to be lots of work coming out from this project over the next 18 months, at least, hopefully 3 papers and a few more working papers. We are also applying for follow-on funding just to sort of develop the physical models, have perhaps more behavioral market responses, and also adding a macroeconomic layer to the financial economic loss. So at the moment, we just have that very direct first order effect on financial losses, but this can have a broader economic effect. And of course, we want to develop NESI as Tony outlined. So look, I'll wrap up there and thank everybody. Nisha, do we have time for a couple of questions? Shall we look at the questions? Over to you.
Yeah, thank you, Ivan. We've got one question on the QA doc, so I can definitely get that one out for you. So this is from Alex Pletzer, who's at NESI and NEVA. Are you considering cascading effects, for instance, flooding causing electric power interruptions, which in turn can cause other damages?
Yeah. Go ahead, Tony.
I mean, I can make a start with this one. We're not explicitly considering that, though. In the carry space, we are considering infrastructure as an asset that is under the exposure objective. These are assets that can be damaged by hazards. So in that kind of relative sense, we are considering infrastructure and its effect, but not directly.
Yeah, and I would say in the other parts of the modeling, no. And so obviously infrastructure is clearly important. Yeah, so, and I mean, if you think back to the theoretical diagram I showed you, and we talked about the behavioral response to houses becoming stranded well before permanent inundation, there's a very high probability that even before then infrastructure gives up, right? So yeah, but there's our focus ultimately is on the banking and banking stability. So yeah, our focus is not on the infrastructure but the houses.
Thank you so much. I can see one question from Roy on chat. Have you considered modeling across agricultural and horticultural land?
I think so. I refer the honourable gentleman to my previous answer. So look, I think it's hard enough just looking at real estate. So yeah, I think the Reserve Bank have looked at sort of physical risk on the agricultural side. The second largest item on New Zealand Bank's balance sheet are perhaps unsurprisingly dairy intensive agricultural loans and other agricultural loans. But no, we're pretty much focused on real estate. What we would like to add, for instance, is we've been very much focused on coastal flooding, but some other modeling by some other agencies suggests that fluvial flooding might be bigger potentially. So yeah, and actually interacting the fluvial with the coastal.
And I'll just add to that, there's a carry aspect to this one too. So valuable agricultural land is also under the exposure set of criteria.
Thank you, Ivan. Thank you, Tony. With that, we're coming to the end of this webinar. I want to do a very quick wrap up. We are way past the time, so I don't know am I sharing the right screen? Maybe not.
Yes, we can see your screen.
Oh, okay. Well, I have to share this one. Yes. So just to very quickly wrap up, what we heard today was about the STRAND project and the NESI consultancy's work into bringing this together so far. So if you're interested to know a bit more about this, or if you have a project that you think we can help with, please contact us at support@nesi.org.nz. We have a team of research support software engineers who provide quite a lot of support to projects. So reach out to us. And thank you to Quinn for bringing all of this together, to Ivan, Anthony, Murray, and Maxine for taking the time to present. We do have a training mailing list at NESI that you can join. We keep you posted on any of the trainings and webinars that come up. And if you have any questions or feedback, we'll be sending out a post-event mail out soon with the recording and all the links that we've gone through today, as well as a feedback form. So thank you. Hope you have a lovely rest of the day.
Thank you, Nisha. Thank you all.
Thank you.
Thank you.
Cheers.
Thanks a lot.